Okay, I'm going to finish the problems 14 through 28 on buffers. It's chapter 17, and number 13 that we had just done on the last one, we had a pH of 3.36. That would be C. They should only have 2 sig figs there because the Ka was given a 3.5, so you get 3.46 out of the negative log of that. Okay. What's the pH of a buffer solution adding 0.25 hypochlorous and 0.33 sodium hypochlorite? Okay. The equation. I would start off with the hypochlorous acid reacting with water produces the conjugate chlorate. You get 0.255 and 0.33 initially, so you know it's a buffer. So you go to Henderson-Hasselbalch, the negative log of your Ka, 3.8 times 10 to the negative 8th, plus the log of the chlorate over the hypochlorous, that's a chlorite, 0.33 over 0.255. Because that's greater than 1, that should be increasing your pH towards the basic side. So the negative log of that is 7.42 plus 0.116, 7.536, and I get 7.54, and that corresponds to E. 15. When it comes to buffers, interestingly enough, you could start with chlorate on the left of chlorite. So you could have chlorite reacting with the water, making the hypochlorous acid and the base, OH. It would work fine. You'd have to use the POH equation. So you'd have POH equals PKB, and it would be reversed. You would get the same exact answer. So in case of buffers, you can use either, but that would be more work to start with the base. Another one, acetic acid and sodium acetate. You get 0.818 and 0.172. You plug it into Henderson-Hasselbalch, 7.52 plus the base is 0.172 over 0.818, so it's minus 0.677. Answer I get is 4.075, which is closest to A, 4.077. Formic acid with formate, again, I would just call it HFOR and save all the work, and formate, FOR. The sodium is a spectator, so you get the weak acid HFOR plus water making hydronium plus formate. What's different about this one is they gave you 0.37 moles and 0.23 moles, and then they told you to dissolve it, so your molarity is divided by 1 molar divided by 1 molar. I'm going to leave it like that to show you something that happens in buffers. pH equals negative log of your Ka plus the concentration of formate over HFOR. Okay. Negative log of 1.77 times 10 to the negative 4th is 3.72, 3.752. And then what's interesting about this is if you did a dilution, the liters cancel out. So no matter what I put, you really can just put moles over moles, and it works. And buffers are unaffected by dilutions. Okay? It's not going to change it. The ratio stays the same, okay, mathematically. You get 3.752 plus a negative 0.21 because the base is lower. This is fractional, so it's going to be negative. 3.542, I would say 3.54, and so C, 3.55 is the closest. That problem's only 2 sig figs because the concentration of formate is 0.37, only 2 sig figs. Okay. Let's see. K of acetic acid. This is a little different. The pH of a buffer is combining. They're putting milliliters and the molarity, and milliliters and the molarity. So it's almost like it's not really a reaction. It is a buffer. Okay. So I have HAC plus water making H3O plus AC. But if I look at this, 50 milliliters times the molarity gives you 50 millimoles. 50 milliliters times 1 molar gives me 50 moles. The 2 millimoles are equal, and then if you were looking at dilutions, it'd be 50 plus 50. The total volume is now 100. So your concentration is 50 over 100 and 50 over 100. It's the same. The only reason I pulled this out is to show you the same effect where when I plug it into Henderson-Hasselbalch, I get 50 over 100 and 50 over 100. The 100s end up canceling out. The 52s end up canceling out. You get the log of 1. And the log of 1 equals 0. So the pH equals the pKa, 4.754. That plus 0, 4.754. Okay? And now we're going to play on that theme where when your conjugate base and your conjugate acid are equal, the ratio is always equal to 1, and the log of 1 equals 0. So pH ends up equaling pKa. Okay? This is the converse of what we just learned. If pH equals pKa, then your HA, your acid, has to equal your base, C. The pH is 4.74, which of the following is true. I can kind of look at this and see that the pH has been lowered, increased to 5.3. So that tells me that the base is increasing. And it would tell me that the base has to be greater than the acid. Now, I could use Henderson-Hasselbalch, solve it down for my ratio of HA of base over acid, and what you get is this number is positive. Okay, so if that number is positive, that means the base has to be higher than the acid. Okay, this is just the opposite. In this case, from the get-go, your pKa is 4.75, your pH is going down to 3. So now you have to have more acid. So actually that's wrong. That answer should be A. The acid should be greater than the base in this problem. Okay. If I did the same math solving for the ratio, I plug in my numbers, it comes out to be negative. So the anti-log, to get this to be a negative number on an anti-log, that means your fraction has to be less than 1. So it means your denominator has to be greater than your numerator. So the acid will be greater than the base. That's that answer. You have equal amounts of salt and acid. Again, that's going to be the log of 1. It's equal to 0. Your pH equals your pKa. So that equals a negative log of 10 to the negative 8, which is equal to 8. 22 is D. I guess there was only 24 problems on this. That's a break. On the basis of this information below, you get a pH buffer of 9. Which is the best one? Well, if I go back to saying my pH equals my pKa, at a maximum buffering, this will always come out to be a log of 1. That is, the two conjugates equal each other. So your pH equals your pKa. So if I solve down for Ka, my negative log of Ka equals 9. Log equals 9, negative 9. So my Ka ends up equaling 10 to the negative 9th, and that is closest to H2PO4, 8 times 10 to the negative 8th. Okay? And I would choose, if I looked at the equation, the H2PO4 acting as an acid will react with water to produce its conjugate H2PO3. So I'd say those two things are what I want in there to get a pH of around 9. And the same thing, which is the best buffer? pH equals pKa. Your log's going to be equal to 1 because the the base will equal to weak acid. Okay, so if I take it and solve for the Ka, we're going to put in a 4.20. That's what we want to get. Solve it down to negative 4.20. Take the anti-log. 10 to the negative 4.20 equals 6.3 times 10 to the negative 5th, and that gets us B. All right, we should be ready for a quiz, or an assessment, I'll say, on Chapter 16 and Chapter 17 now, and that's going to be the main place where I'm going, and then we're going to start a new chapter, Chapter 10.